I try to write in a bigger letter, definitely. But from your side, if you can actually come closer to this, you will be able to see what I write actually. Okay, that's my request. Okay, so let me just switch gear and try to see whether I can get more information about proton. Okay, so what I'm going to do today in this part of my course, I will look at what is called deep inelastic scattering. Okay, so let's see how I going to discuss about this. So deep inelastic scattering experiment, unlike this elastic, okay, it's inelastic. Okay, that's the only difference. Deep, I don't know why it is deep, because probably it is actually probes this proton very deep inside and things like that. So it's called deep inelastic scattering. So the picture looks something like this. Okay, maybe I can write slightly bigger. Okay, so you have a lepton coming here, this time with lots and lots of energy, P prime, P. So it's coming with so fiercely, it's so fierceful that it will break the proton into pieces actually. Let's call this bunch of particles X. The total momentum I call Px. Okay, you can have P1, P2, P3, P4, etc., etc. All kinds of particles that are produced. Okay, this is proton with momentum P. Okay, this is photon that is exchanged. Again, the momentum transferred is actually Pe minus Pe prime, simply this. Okay, this is how the amplitude for the scattering process looks like actually. The only difference is proton doesn't go to proton itself actually. It gets broken into pieces. Okay, let's imagine, suppose that such an experiment takes place and it breaks into pieces actually. What you see is a bunch of particles, the particles that are discussed in the morning actually, pions, rho mesons, and lambda baryons, and all kinds of hadrons. Sometimes it could be leptons also, Ws, and all kinds of particles. Anything that is broken, because Einstein told us actually if you pump in energy and break it, it will be converted into some masses. Okay, that masses could be anything. It could be electron also. Okay, some energy is converted into masses. So these particles that are produced could be anything. Okay, as long as physics is, all the laws of physics are respected, energy and momentum. Okay, this will be, so all kinds of particles will be produced here. Okay, such a experiment, thought experiment I call deep inelastic scattering experiment. You'll see that such an experiment can be performed and you can really see this happening. Okay, so for currently I consider this as some theoretical exercise. So the cross section for this process, very high energetic scattering of this kind, okay, will be, again, you can write down the cross section as flux part, because it's, I'm not choosing any specific frame. The incoming flux would be more like P square minus m square power of. This is the flux factor actually. Any textbook that you read in field theory will tell you this is the most general flux factor of 2 going to many particles. And then you have a matrix element for this process. Okay, this matrix element or the amplitudes could be different because I don't have a final state. That's just the proton actually. It's a bunch of particles. So final states are different, so amplitude could be different. Okay. If I write too big, then I won't be able to fill up anything. I'll fill up too much. Can you come closer actually, because there are so many free. It's a win-win situation actually. I will try, because if I start doing it, then I will mess up everything. It is easier for some of you to actually come forward. How many of you cannot see? Or I need a backed chalk piece, or I will certainly write actually. I'm trying, but okay. So this matrix element square is going to be different from what I wrote down earlier. And this is the phase space for 1 plus n particles. So this is the bunch of particles that are produced, say let's say n number of particles produced, and with one lepton in the final state, 1 plus n particle phase space. So it is just the product of phase space for the individual particles and times total energy momentum conservation. Let me write down what this is actually. So the phase space for this dps n is actually product of, okay, let me just write down for lepton part d cube p prime 2 pi whole cube 2e prime 0. This is for your lepton in the final state, phase space, and then you have a product of the hadrons that you see in the final state. Okay, this is just the product of, if there are n number of hadrons, hundreds of them, and you just multiply, have this product of hundreds of them, and then there's only one energy momentum conserving delta function, because energy momentum conservation is only one relation actually. E plus q minus sum over ei, I is equal to 1 to infinity, or if it is n number of particles, it's n number of phase space. Okay, so it's, in this case it's n. Okay, so I leave it here actually. This is n body phase space, so I put n. N could be any number actually. Okay, I'm not specifying anything. Very good. What about the matrix element for this? Matrix element for this is the amplitude for electron, proton going to electron, and n number of particles in the final state. Okay. How will I write actually if I have n number of particles? There will be hundreds of amplitudes actually. So this is the most general way of writing this and most elegant way of putting them. It's actually the leptonic part is this, gamma nu, u of Pe, and this propagator which is sitting in between, q square plus I epsilon or whatever. And then this for the proton, Pi prime, Si prime, J mu of 0. Okay, so this time I'm a little more cautious. I mean, I'm not assuming anything, for the proton, that it is not point-like or anything. Just write down matrix element. All my ignorance is hidden here actually. Not giving a parameterization for this in terms of F1, F2. This is just electromagnetic current that couples to the photon, okay, responsible for producing this n number of final state hadrons actually. So this is a transition amplitude for proton going to n number of point-like particles, n number of hadrons in the final state, hadrons or any bunch of particles. This is the current, electromagnetic current. All I know is this current is electromagnetic current, because, but I don't know what is the form of the current. Can I write down as u bar gamma mu u? No, I don't know. I don't know whether I can write in terms of form factor also, because I have many final states that are possible, and each of them having a momentum Pi and spin Si, and it's impossible to write down a most general current that I can think of for this particular process. So I don't know this. I don't know much about how to parameterize. In terms of this invariance, so how many form factors that I need, how many invariants I need, it's completely ill-defined. It cannot be defined, cannot be said. So this quantity, as far as I know, contains all the ignorance that this part of the board contains actually. Okay, is this clear to everybody? So I'm not making any assumptions actually. Okay, unlike proton going to proton case, where I could parameterize this matrix element of the current as F1 and F2, I cannot do this here because there are too many momenta in the final state, and it's not possible actually. Okay, wonderful. Then I'm going to proceed. So let's proceed actually. Calculate this matrix element 1 by 4. This is a polarization average. Okay, if you calculate this, you will get the square of this part actually. You use this part complex conjugate. That gives me this trace of the one that I had written down, P plus M gamma nu prime. Let me just write this gamma mu. This is from the electronic part. Okay, and then we have 1 by q power 4. And then you have, for the proton case, sum over S. Okay, the square of this, this times this. So I have sum over all the S prime and then Pi prime, Ps. Okay. Okay, something like this you have actually. Something like, sorry? Beg your pardon? SI are the spins actually. So if I'm not mentioned actually. So they all contain information about this is the proton spin. Each of them will have a spin SI. So I need to sum all the quantum numbers. Okay. So when you write U bar and things like that, they come with some polarization. S is equal to plus or minus half. Okay, that need to be summed up. Okay, so I need to sum up all the polarizations, average the initial polarization by half. Okay, so you can do this. So this is an honest to good attempt one can make to write down an amplitude without making any assumptions about the proton. Okay, this is fine. Any questions here? Visible? It's okay, thank you. So this part I can write it as L mu nu. Okay, it's a function of what? Q. P comma Q 1 by Q power 4, and then this part actually 1 by 2 sum over S sum over P prime S prime. Okay, I need to do this P prime because I'm doing this S prime PS. When I took the complex conjugate, I did not put star on this current chain. Okay, why is that? Any reason? You can tell me during dinner time. So why I did not put star here actually? In principle, I should put, but take a complex conjugate when I calculate M. I should do this actually. I didn't do it. Very good. So this is the phase space and this is the integral. So I put together, let's look at how the expression looks like. Okay. And if I do this, then d sigma is 1 by, instead of writing full expression, I put to this L mu P comma Q 1 by Q power 4. Okay, times, I'm going to make some definition for this, sum over S prime. Okay, so Ps G mu of 0 Pi Si G mu of 0 Ps. Okay, and then I have a phase space integrals. I will also write down product of I dqpi by 0 times 2 pi whole power 4 delta 4 p plus q sum over I pi. Okay, this is one. This entire thing is multiplied by this, the polarization tensor for lepton. Okay, so you have a lepton part corresponding phase space, the hadronic part with the corresponding phase space, and then this overall energy momentum conserving delta function. Okay, good. I'm going to call this entire part, okay, by some name, okay, to make my life very easy. Because once I accept my defeat that this is not going to be very easy to evaluate by any means, okay, let's assume it and give some name for this, and then let's see whether that using that definition I can make some progress actually. Is that okay? I can do that. So I'm not calculating this, but I'm naming them, find them some name. Okay, it's a second rank tensor because it has two indices mu and nu. So I put two indices called by W. Okay, what is the functional dependency? If I integrate all the pi's, okay, and sum over all the s and s primes, what is the dependency that it will be left with this function? What is the dependency? Is it a constant or it depends on some quantities? Momenta. What are the momenta that it will contain actually? Huh? P proton and Q. Anything else? Huh? Spins are summed, everything. So it's only function of P and Q. This looks very simple function. Second rank tensor having dependency on two momenta P and Q. Okay, once I have pulled out this mu and nu dependency, this rank, this tensorial structure, what would be the dependency inside? Actually, it will be only dot products of this momenta, invariants. So it can be P square, Q square, P dot Q. These are the only dependency it can have actually. Okay, P square is anyway constant, anyway I'm just ignoring that. So it will be only function of Q square, that is the momentum transferred to this vertex, and the dot product, which is P and Q. Okay, that's all. If I know how to parameterize this, then I can make progress actually. Okay, otherwise I'm stuck. You cannot proceed further. So the answer that I can write down for this is 4 times flux factor times L mu nu P times Q 1 by Q power 4. I don't know whether I've left out some factors and things like that. I'm dropping this m square dependency. Let me just make it little more nice looking, times this dq pe prime 2 pi whole cube 2 pe prime. Okay, this looks much nicer compared to the previous one. I'm sure all of you will agree with me that this is much better than what I had before actually. So deep inelastic scattering experiment cross section now actually factorizes into how many parts? 3 parts. Okay, a part containing purely leptonic, which is the top portion of this diagram, square of the top portion, purely leptonic. You know? And a part which contains purely hadronic, which is W mu. This does not know anything about somebody hit him or not. Okay, so it's a purely hadronic part actually. And there's a part which contains information about the mediator, this photon here. The q square, 1 by q square is actually the propagator for this photon. The square of this because it's a cross section that we are looking at it. So it factorizes into 3 parts actually. Leptonic part, hadronic part, and the intermediate part actually. Okay, intermediate part anyway is very simple. Leptonic part is also as simple as that. The most difficult part is the hadronic part actually. Okay, which tells you about how proton breaks into pieces. Okay, and what is the total probability that a proton breaking into pieces, giving you certain number of hadrons in the final states. That's the information that this piece is contained actually. Okay, now once it is broken, it is like you say make some savings in some form. We break it, you know how much you have saved actually. Okay, like that, this understanding this function would probably will tell you about whether Gell-Mann was right or wrong. Okay, we are going to do that actually. Whether this. So if I give it to an experimentalist, please measure this W mu, they will offer to you actually. What is this nonsense? How can you measure this quantity? So you'll have to express in some nice looking form. And if they measure something, that should be giving you some information about the structure of the proton. So that's my next exercise. How I'm going to present it to the experimentalist. Like the way I presented my cross section in terms of F1 and F2, this also I'll have to present it in a way that by measuring certain unknowns hidden in this W mu, I should be able to unravel the structure of the proton in this particular scenario where proton is bombarded with a very high energetic electron and where proton gets broken into pieces. So that's my task actually. So it's motivation is clear to all of you, I guess. Okay, so how I'm going to do this actually? It's not very difficult because we theorists should know how to again parameterize this quantity. Okay, in terms of some, instead of giving an expression which is a second rank tensor, you give something much more sensible actually. So how do I do that actually? Okay, before I proceed, I wanted to make little more progress with this. Instead of saying every time W mu is this, I will make one nice looking expression that you have seen this morning actually in Marco's talk, but I will again do it for you so that it will be useful for you. So I'm going to do this. You start with this expression, okay? You start with this. Replace this delta function. So I'm going to work on this W mu part actually and give you a simple looking expression. So this delta function, okay, you can represent it by some integral of an exponential, right? What is delta function of e power ikx integral over x is delta k, right? Like that, you can actually write down this integral as integral d4 psi e power I p plus q minus sum over pi. This is nothing but this delta function actually, 2 pi power 4 times this. Okay, so I can replace this delta function by an exponential, okay, which brings me an overall exponential d4 psi e power I P plus Q minus sum over I Pi times psi. That's first step. Okay. Then the remaining ones remain as it is actually. Okay. This is sum over S prime, Ps, J mu of 0, Pi Si, J nu of 0, Ps. Okay. This remains as it is. Hopefully I have not left anything. And then there is a phase space integral. Okay. Product I dqpi by 2 pi t 2 pi prime. Okay. This is all I have done actually. I have just replaced this delta function by this exponential representation. Now, note the following, that if I can write down e power I p of xi j mu of 0 e power I operator, where p is the momentum operator because it's a field theory, okay? And sandwich between ps and pisi. Okay, what will you get actually? I take this operator and I'll do this. For this p, when it acts on this, will give you the eigenvalue of capital P, which is small p. And this p, when it acts on this, will give you pi. Okay, and I have a bunch of pi's here actually. So it's going to give me sum of pi's actually, product of e power pi's, okay, which will be exactly this term, e power ip minus integral e power sigma ipi. Okay, so these two terms, I can bring it inside and write it this way. By writing it this way, what do I gain? You know, this quantity by translational invariance simply becomes Ps times j mu of I pi si. Is that correct? So you can actually absorb this P and sum over pi and into this current using translational invariance and write it this. So you can actually remove this part and replace this 0 by xi. So that is the first step I'm going to do. Very good. That's an important progress. It's always good to actually proceed, no? Instead of say, okay, I'm happy with this and leave it. So I'm proceeding in that fashion. Okay. So d4 psi e power I q dot x q dot psi times ps j mu of psi pi si I could do only for one current actually, okay? Because there's only one exponential I have. Okay. And then product of I d cube pi by 2 pi cube 2 pi. Okay. So this is what I get actually. Some integrals I get again. Looking better now. Okay. Much better than the one that I started with. Okay. Still this PIs are hanging around. Okay. And the beginning I said actually that we produce final states which are bunch of hadrons, muons, pions, everything that are possible. And I'm inclusive cross section that I'm computing. So I'm summing, I have to sum. That's why that phase space integral is there. dqpi, gqpi, and things like that. I'm sorry, it's not pi prime actually. You can, what did I use actually? Let me just check. So I call this, all of them are pi primes actually. This is bunch of pi prime. P is the initial, no? So anything outgoing is prime. So we put that pi prime here actually. Okay, thank you for pointing out. Okay, this is good. This is good. This is good. Just a notation. Is it okay? So final states are with primes, like lepton is a prime. Now you see this, carefully stare at this part, okay, except this and this phase space. Rest of them are independent of these final states. Okay. This and this. Okay. Because I have pulled out everything. Okay. So this is nothing but in a completeness relation, right? So you can set this entire sum over Si pi with the phase space. With this insertion, I can call 1. So it is simply this identity that I am using. Si prime, product of TBI times is 1. So you can just drop it actually. So it's worth an exercise to go over this, 2 or 3 steps, okay, to get an expression which is simple looking than the one that I had earlier. So if you do this, then what you get actually, I can drop this part and I get this following result actually. Integral. So I think it's important to actually keep track of some, I don't know, this whole thing I call W menu, but it is actually called 4 pi m times W menu, okay? That's some definition, okay? It doesn't matter, but we can always put it to be consistent with the literature. If you do this, then I get something like this actually. What is it I get? 1 by 4 pi m into d4 psi e power I q psi ps j mu. Okay, I'm running low. J mu. Okay, so isn't it much better looking than the one that I had actually, where I had a lot of sums, final state, all that blah blah things. All of them are gone actually now by simply by using these 2 things. One is translational invariance that I used here. Number 2, I used this completeness relation because I'm calculating inclusive cross section. Sum all the final states. I don't care what it is produced, elephants or dogs or cats, all of them are summed up actually. So I don't have any information about the final states. This is completeness. So it's 1, gone. Having done that, I get an expression for W menu, which looks very, very elegant actually. It is just simply Fourier transformation of matrix element of product of 2 electromagnetic currents, but situated at 2 different space-time points. Okay, not at the same point. Okay, if you recall, this is what Marco actually showed in the morning. Actually, started with this formula that you have a W menu which is expressible in terms of certain Fourier transformation. Now you can see dependency is very clear actually. This is Q and the P here actually. Everything is integrated out. Very good. So what is the next step? Okay, this will be very useful later on actually. You'll see repeatedly this representation. Okay, so a cross section now is this, and the W menu now has got a better look now. Okay. So now how do I proceed this actually? I don't know how to calculate it. Why I cannot calculate it? I don't know how this current J acts on this proton state. Okay. If I know how J acts on this proton state, I know how to calculate this quantity. At the moment, I don't know how it acts. I don't even know what is the form of the current, whether it is psi bar gamma mu psi or some scalar field phi del mu phi. Nothing. All I know is actually it transforms like a vector under Lorentz transformation. Beyond that, I have no idea actually. It's real. I did not put star here, so it's real. It transforms like a vector under Lorentz transformation. Beyond that, I have no idea, unless I assume that proton is made up of point like fermions, or a point like bosons, or a point like spin 1 particle, spin 2 particles. I cannot make any statement about this actually. I cannot calculate this. That's the fact. Okay. Having realized that, how will I proceed actually? The way I can proceed is the way I proceeded for the form factor. So I am going to use this property that it is a second rank tensor. I'm going to parameterize them in terms of some unknowns actually. Okay. So before I do this, I should actually have complete understanding of this. These changes are real. So W mu nu has to be real actually. Okay. By calculating the Fourier transformations, it should be only a function of q square and p dot q. So it's a real function of p square and q square actually. Okay. Number 2, the currents are electromagnetic currents. Okay. That is the only thing I know other than these transmission properties. Which means if I multiply Q, what is electromagnetic property? The property of electromagnetic current, it's conserved. Okay, otherwise charge will not be conserved. Okay, which translates to the fact that if I multiply Q mu or Q nu on this, it should be 0. Okay, right? If I put it inside this derivative, you can easily show that Q mu times W mu nu or Q nu times W mu nu has to be 0. Okay. So we have some information about this. It's not that we are completely ignorant about this function. That is one thing. And I also know it's function of Q square and P dot Q. Okay. Now I'm going to construct a second rank tensor satisfying all these properties. That's the only goal now I have. So how do I do this actually? So I write W mu nu as, parameterize them, W mu nu. So the simplest second rank tensor is minus G mu nu or G mu nu, and then W2 times P mu P nu. This is also second rank tensor. Everybody would agree with me. And then this is Q mu Q nu, I think so. This is also second rank tensor. W phi P mu Q nu plus P nu Q mu. Okay, so what are the properties that I used? Real, okay, current conservation, okay, what else I can use actually? I can, it's a second rank tensor, Lorentz property, second rank tensor. Okay, I can also use properties like parity, time reversal, all that. Okay, we should not actually leave out anything that we know about it actually. Okay, this is a scattering experiment where electron scatters on a proton producing bunch of hadrons. Okay, do you expect parity being violated if photon is exchanged? No, because it's photon exchange, so parity has to be conserved. Electromagnetic interaction. Electromagnetic interaction respects parity, symmetry. So I can use this symmetry property actually to time reversal. All these processes are a time reversal invariant actually. You're not violating anything. It's you can either multiply on Q nu or Q nu. So you can always shift this Z to minus Z by translation invariance, and then apply derivative on this and get Q nu. Okay. So it doesn't matter where this is actually. You can always use translation invariance to move this psi to minus xi here actually. Very good. So I've used this, current conservation, parity, time reversal. If I break parity, what will happen actually? You'll have to add more terms. Agree? Can you give any tensor which you can parameterize the violation of, which is not parity conserving? Huh? Epsilon mu, very good. So you can add some term like epsilon mu nu Levi-Civita tensor, which inherently does not preserve parity. Okay, so I'm not adding such terms here when I parameterize this. So these are the only 4 terms that I can write down that that respect this, all these things that I considered here actually. Okay, so it has got these 4 of them are functions of p square, q square, and p dot q. So all these functions, I is equal to 1, 2, 3, 4, all of them are functions of this actually. Okay. So far I have not used current conservation, because if I multiply q mu, this is not 0. This is not 0, this is not 0, this is not 0. So I have not used current conservation. Now if I use this current conservation here, okay, now if I just substitute this in this formula, okay, I get 2 identities, because there are 2 equations, 2 identities. One says W5 is related to P dot Q by Q square. This is a very, very elementary exercise. You can try in your leisure time. W4 is equal to P dot Q whole square by Q power 4 W2 plus M square by Q square W1. So these are the 2 relations. So W4 and W5, if we apply a current conservation, they are related to the other ones like W1 and W2, which means we don't have 4 independent, W's in our problem. We have only 2 of them actually. The other 2 are derivable from this. So finally you get W mu nu is equal to, write down W1. If I put it back, let me use the board more economically. So W2 by M square okay. So this is how it looks like actually. So I've reduced the problem of computing this cross section into, only to these 2 functions unknowns. Like in the form factor case, we have F1 and F2. Now in the case of deep inelastic scattering, again you have 2 functions, F1 and F2. Why these 2? You'll have to go back and convince yourself. Okay, that's also a good exercise actually based on some independent amplitudes that this process can have. Okay, this number 2 is not actually accidental. It is related to the number of independent amplitudes that we require to express the cross section actually. Okay, in the case of unpolarized deep inelastic scattering. Okay, so there are 2 structure functions. Okay, I should mention the name actually. These W's are called structure functions. Okay, so they are not like form factors. Form factors are defined at the amplitude level. You write down the current in terms of F1 and F2 or GE and GM at the amplitude level. So they are actually carrying information about the spatial structure or momentum structure at the amplitude level actually, okay, that you extract them. This one, W1 and W2 that we extracted, after squaring the amplitude, we found that this product of 2 currents are expressed in terms of this 2 structure functions, W1 and W2. Okay, and this is much more useful formula than the other one. Now if I substitute back here actually, like I did in the form factor case, if I substitute back, then I will get a nice looking formula of this kind actually. So that's what you get actually. I can proceed here actually. Okay, so what do I get actually if I calculate d sigma by d e prime d omega? You get exactly this same nice looking formula for alpha square e prime square by q power 4. Okay, so you get a W2 into sine square theta L by 2 plus 2 times W1 q square p dot q this is sine square L by 2. Okay, so the same exercise, you multiply L mu nu into W mu nu. That will give you this cos square and sine square. And this phase space part will become d e prime by 2 d omega prime. I've just taken out d e prime, d omega prime outside. The remaining is this. So it's a very, very simple looking formula. Easy to derive actually, the way I did it in the last class. So the formula looks very much similar to the formula that I got for the elastic scattering. Okay. So the only difference is in the elastic scattering case, the both W1 and F1 and F2, they depended only on Q square. They did not depend on P dot Q, if you recall, right? Is that right? It's not dependent on P dot Q. We have now P dot Q dependency, okay? So what you are going to extract here, if I give it to an experimentalist to actually perform an experiment, deep inelastic scattering experiment, and extract the coefficient of cos square and sine square, and those functions, if they plot it as a function of q square and p dot q, they will have an explicit dependency. Okay, so it's going to give you more structure than what a form factor can give. Form factor can give only dependency on q square. You can Fourier transform and study spatial structure. But this one is much more interesting because you have broken the proton into pieces, and if by studying this structure functions, you might get more information. Okay, that's one aspect. Now I'm going to give you, okay, up to this is clear to everybody? Okay, so this is the more, what you call useful formula for doing an experiment and getting an information about the structure functions. So now I'm going to sort of not stop here, but I'm going to relate it to something and find something very interesting actually. That is where I will stop it actually. And I request a few more minutes actually to bear with me. So that will happen actually. Okay. So let me now theta L by 2 lab frame actually. Very good. So I'm going to, so far so good. We have now inelastic cross section expressed in terms of two structure functions. Each of them is dependent on two kinematical invariants. One is q square, other is p dot q. That's the lesson that we learned so far. Okay. Now, in between, of course, they are not calculable because as I said, actually, the currents are not known to us. We don't know how the current acts on the proton state. We don't know how to calculate the matrix elements. We don't know how to calculate. That's the blind statement. Okay. Now in between, very well known how many of you heard this name, Bjorken? You heard this name, Bjorken? Most of you? In some context you must have heard. Okay. So you was the one who was actually, other than other people actually, David Grass, Callan, Sutherland. There are many people actually in those days who were working on this process, because it's a very interesting process actually, in physics. Actually, it revolutionized our understanding of not only strong interaction physics, there's many other things. Okay. So he studied this process, okay, without using any specific model, like proton is made up of quarks and gluons and things like that. Nothing. That time there was no clue about gluons. Okay, there was information about quark and things like that. He did not make any such assumption. He did not imagine proton is composite and things like that. All he did was actually, being a theorist, he just looked at this current, in particular this W mu as a function of this, and see whether you can make progress. Okay, what progress you can make so that you can make statements about this function. We made a statement about this function in terms of W1 and W2. Okay, all the ignorance of these matrix elements are hidden in these two functions, W1 and W2. That is all we could do. So, but Bjorken actually made a little more smart move. What is the move that he made actually? So he considered that particular correlator and studied in a particular limit actually. The limits I call limits. Okay. Okay. So you consider this a limit consisting of three statements. One, the q square that is appearing in the form factor, okay, structure functions, is very large, infinity, let's say, theoretically. And then the other dot product, p dot q, which is also w's are functions of this, very large. And keeping this ratio fixed, a particular ratio, q square by 2p dot q, you fix this to be fixed. Okay. He wanted to study this actually. He did not assume any model. He did not know how to compute. He doesn't know what is the form of psi. Psi is just a function, like, if I say, some r of x, unless I tell you, you don't know what it is. Okay, like that size, for him, J mu is just a current satisfying some nice properties. Otherwise, it didn't have the form of the current. Okay, but you can still proceed. Okay, you used something called current algebra. Very similar to the symmetry that Gell-Mann used. Okay, symmetry that related, states. Okay, it's called current algebra, which relates currents. Through some continuous symmetry. Okay, let's not worry about it actually, because this is some ancient physics that we are not keen to do. Let's assume that he did something. Okay, what he found was actually in this limit, found two interesting things. One, that if you look at this, this, let's say I will not put, let's call this is Bj. This LTBj means these three set of things are fulfilled. LTBj of M W1 of minus q square, which is q square, p dot q, or I can also put q square if you don't like it, q square equal to, we found that it's no longer a function of q square and p dot q separately, but it is a function of this ratio. Found that it is independent of q square and p, but it's only a function of q, the ratio q square. Take any value of q square, any value of p dot q, as long as they are large, the ratio is fixed, the structure function depends only on this. That's an observation. It's not an obvious statement that you can make actually about two variable functions. Okay, if it is f of xy, you cannot say, okay, it's only a function of x by y, unless there is some strong reason behind it actually. So it's a very strong statement coming from a field theory. So I would consider this is one of the breakthroughs in strong interaction physics that changed the way we look at, hadrons. Okay, and we should give full credit to Bjarkan actually. Okay, I'll tell you what is the consequence of this two statement that he made. Okay, which really changed how we look at proton. So this is the very famous relations that he actually came up with. It's called Bjarkan limit, and this fact that this W's and W1 and W2s no longer independently functions of two variables, but only function of this one single variable called xbj. Okay, and we call this entire thing is Bjarkan scaling. Okay, this is purely theoretical actually, just based on certain assumptions about the currents, electromagnetic currents, which are well valid. Okay, there are no issues with that. By using this, you can show this actually. Okay, so this was his observation. So I will not tell you how we got it actually. If you are interested, you can look at the original paper. All you need to do is actually take this expression, okay, assume these are electromagnetic currents, okay, and study large q square and large p dot q limit of this by looking at certain properties, analytical properties of this function actually. Okay, you can show that it is not independent of these two invariants, but it's only dependent on this ratio. Okay. Okay. If I tell the mathematician, very nice actually. It's about a complex in an integral Fourier transformation. It's about this statement, but it is not a very trivial statement for physicists actually. Okay, saying some function which is originally dependent on two invariants now become function of only the ratio of these two invariants. It is a profound consequence. Okay, and what is the profound consequence actually? This profound consequence is about, okay, the deep inelastic scattering in a particular limit, okay, now has a property called scaling, meaning that while it's supposed to depend on these two independent invariants, now it depends on one. Okay, so something is actually gone away. So something is gone and it becomes a scaling. Okay, it's like if you have a theory where there are two dynamical degrees of freedom, but in some limit actually it behaves as if it has only 1 degree of freedom. Okay, which is enormous change to the system, and it must tell you something about the internal structure of the system, right? If you say that there are no mass scales, it means something actually, right? If there are no massive particles in the system, it means something actually. Okay, so it's like that actually. So this scaling actually has a very deep interpretation. I don't know, if you give me some more time, then I can tell you what is that interpretation is. Okay, and this is the birth of what you now call pattern model. Okay, so the picture now has changed because of how people looked at proton is now changed simply because of this very beautiful observation. This is called Bjorken scaling. Okay, before theorists actually go and start interpreting this and constructing models that actually can have this property, it's important to actually go and check whether this is indeed happens in experiments. Okay, I have a slide I'll show you tomorrow morning actually. Okay, this experiment was performed at SLAC. Okay, and people looked at this cross section that I have written down as a function of q square and p dot q, extracted w's as a function of q square and p dot q, and considered the region where p square and q square are very large with the ratio fixed, Bjorken limit, and found that structure functions in fact scaled as Bjorken observed. Okay, that was an enormous, I would say, success in the understanding of this structure of proton, because scaling was established in an experiment and everything was based on actually certain assumptions about analytical structure of this current, product of two currents. So I would call this is one of the breakthroughs in high energy physics, and why that is important that we have to see. If findings of somebody showing scaling and experimentalist measuring that it works, it's not the end of the game actually. Okay, but it brought very beautiful physics out of it. That physics is basically goes by the name pattern model. Okay, so how do I have more time actually, or else should stop?
Basically, the second homework I gave you this morning is proven here.
I proved.
If you want, I can go again through the, I prepare some slides.
I can take 5 more minutes. Everybody is tired. If you are really excited about this result, what I'm going to tell you is much more exciting actually. Okay, so if you have little patience, I can explain to you. Okay, so let me just try to show this in 5 minutes, let's say. Del square sigma by d. So let's 4 alpha square, e prime square, q power 4 times. So it is in the limit which Bjorken actually said. Okay, let me just q square, I put q power 4. This is q square. This is q power 4. We all know what capital Q means now. X bj f2 x bj f1 of x bj sine square L by 2. Okay. This is for the DIS. Okay. If proton is point-like, we got something very similar to this. Okay. We had exactly the same overall factor. Okay. We had the same factors here. Okay, if you go back and put everything, bring the delta function inside, you will have this actually, xbj plus 2 by m half of delta 1 minus xbj into sine square theta L by 2. If it is point-like, proton is point-like, okay, more like a. How this term comes actually, if you recall, I had a delta function delta nu minus q square by 2m, okay. xbj is minus q square by 2m nu. It's same as minus q square by 2p dot q, both are same. by bringing nu here, you get, this is xbj. So it is nu, I can take it outside, 1 by nu, 1 minus xbj. So this is how this xbj comes, delta function comes. Okay, if you look at your, the previous lecture. So it's, if it is point like, this is your cross section. Okay, the difference between a point like cross section and deep inelastic scattering cross section is this delta function is replaced by this f. Okay, both as same scale dependent, the scaling variable xpj here, xpj here. It's almost identical, except that the form factor now is a delta function. Correct? Okay. Now, these are different. I mean, one is about elastic scattering, the other one is about deep inelastic scattering. This is on elastic scattering on a point-like object. This is a deep inelastic scattering on a structured object, as form. Proton is a structure. Now, let me just relate, these two, how it is related. Let's relate actually. Let's express this in terms of this. If you do this, you can say d square sigma dis by dE prime d omega is 4 alpha square E prime square by q power 4 times I'll write down here and I'll show you that why this is indeed true. This is my first term. Plus xbj dy by y into f1 of y 4 alpha square E prime square by q power 4 2 by m sin square theta l by 2 delta 1 minus xbj by y. Okay. So let's just look at this only. Okay, I have. So this is a deep inelastic scattering result. This is a elastic scattering with point like proton. Okay, so DIS scattering, just writing as an integral representation, meaning if I perform this integral over y, okay, I'll get back to this formula. Would you agree this? For example, if I use delta function here, perform y integration, it's trivial. Y is equal to xbj. Substitute, you'll get back this actually. So I've written this as an integral of this quantity with a delta function here. Second term I've written as an integral of this with one delta function. This is correct? There's nothing I did actually. Okay. This and this are identical actually. Okay. What this tells you? It tells you that deep inelastic scattering cross section is just integral of elastic scattering cross section times a function which is a function of one variable. Is this clear? And summed over for all y. Okay. So here it's not very obvious actually. The scaling implies that you can express deep inelastic scattering in Bjorken limit as sum of elastic scatterings. Okay. Each one is weighted by a function f2 here and f1 here. So cos square part is weighted by a weight function f2 with one variable, and the sine square part will be weighted by this f. So it brings you a new picture, as you can see, that if it is a single variable, it depends only on one variable. Okay, deep inelastic scattering in Bjorken limit is just some incoherent sum of elastic scatterings, and each elastic scattering is weighed by some unknown function f1 and f2. Okay, so this is the picture emerges. Okay, is unbelievable, to start with, but this is the crux of this pattern model. So now you can actually massage this and start imagining that if this is what is Bjorken scaling tells you, then I can think of proton in the in the deep inelastic scattering kinematics. The Bjorken limit looks as if it's a collection of point-like objects, and this entire scattering cross-section or collection of point-like objects which are weakly interacting, and the inelastic scattering is just the incoherent sum of elastic scattering cross-sections. Okay, this is the picture emerges out of this analysis, and this is the picture that you start with in the pattern model actually. Okay, I hope convinces you that it's a beautiful picture emerges out of a nice piece of work by Bjorken and the confirmation by experimentalists that it is indeed really happening in the experiments. So you can think of as an inelastic scattering as incoherent sum. That means it's simply adding the cross sections for, it is like, you have a collection of particles moving, and they are, in this frame actually, a photon sees this collection of particles as weakly interacting or almost not interacting with each other, and then the photon interacts with one of the particles without even realizing that there are other particles around it actually, and that if sum all these such scatterings, what you get at the end is nothing but your total cross section actually. Okay, so this picture you can fine tune it and sort of make it much more put it in a much more solid ground and call it as a pattern model. I'll write down the formula based on this observation, and this is the one. So why I did this exercise of form factor and point like is not just to sort of have a simple looking formula. It shed light on the structure of the proton at low energies, and also it gives you a feeling of how inelastic scattering can be thought of as a sum of incoherent sum of elastic scattering actually. So this is something which you cannot actually imagine if you just stopped at this stage actually. Okay, because we proceeded so long, we could actually come up to this nice picture. Okay, this picture is called pattern model. I will make it much more rigorous, much more appealing tomorrow, this one actually. Okay. So I'll stop here.